First, I'd like to point out the required disclaimer at the bottom of this title slide. And I'd also like to introduce my co-authors. Tim McAllister, Chris Cleary, and Lieutenant Commander Robin Kawamoto all work for the Coast Guard Surface Forces Logistics Center and have been responsible for most of the work that we're going to talk about. John Dolney works at the ABS Harsh Environment Research Technology Center in Newfoundland and has been leading our efforts for these advanced structural analysis methods. I also want to acknowledge Dr. Claude Daly from Memorial University in Newfoundland, since the methods that ABS is employing and that we're using are mostly based on research that Claude has pioneered. The presentation is based on work completed over the past 5 years on operation of the national security cutters, both in the Bering Sea in the winter and then off the North Slope of Alaska in the summer. Much of the work is focused on the capabilities of the hull structure to withstand ice impacts. It also included a lot of lessons learned related to systems operation in cold temperatures. Since 2012, Coast Guard patrols with non-ice breaking cutters have increased, and they now include winter and summer patrols in the Bering Sea and summer patrols in the Chukchi Sea. Commercial traffic has increased dramatically, as have the incidents the Coast Guard's had to respond to in cold latitudes. The work presented herein was initially started to assess the risks of operating these non-ice strengthened cutters in the marginal ice zone. It can also be applied to future cutters and is relevant for naval combatants. Note again that we're not talking about icebreakers, we're talking about thin-skinned ships. The standards that exist that are referenced by the Coast Guard when we start talking about operations in ice are the Classification Society rules, notably the International Association of Classification Societies polar rules, and then additional rules for thin-skinned ships, such as the ABS Steel Vessel Rules ice classes. The IMO Polar Code incorporates the IACS Polar Class along with a number of other features. U.S. Coast Guard has a very long history of operating icebreakers, and over the years we've developed quite an extensive engineering capability in that area. We've recently worked with ABS to see how our design methods for icebreakers correlate with the Polar Code, and we're continuing to refine our design standards. So the first step when assessing what the capabilities of the ships is to define the environment. And this is focused on ice conditions and air temperatures and in the marginal ice zone. The marginal ice zone moves from in the Bering Sea, South Bering Sea in the winter to off the North Slope of Alaska in the summer. So it's a moving target. This slide shows the maximum extent and the minimum extent of sea ice in the Alaskan Arctic for an average year. These charts are based on NOAA data collected between 1972 and 2007. The purple areas at the bottom are ice thicknesses less than 12 inches, and aerial concentrations varied from 0% to 100%. And that's really what we talk about when we talk about the marginal ice zone. The yellow areas, thickness varies between 12 and 28 inches with high concentrations, 80 to 100%. Green, thicknesses from 28 to 47 inches, high concentrations. Blue, thickness greater than 48 inches, but still first-year ice. And then the red areas are second or multi-year ice with thicknesses greater than 79 inches. So that sort of sets the stage what we're talking about is the ships operating near the purple areas or slightly into the purple areas. In terms of temperatures, can you read this in the back? It may be too hard. The chart on the left shows the normal daily low, average, and high temperatures based on 20 years of data. And these temperatures are taking not at a fixed geographic location. They're taken at the location of the ice edge as it moves through the course of the year. So those are the operating environment we're talking about operating in. These illustrate that the most severe temperatures a ship operating in the marginal ice zone will encounter are actually in the Bering Sea in the winter. That might be expected. But still, even in the summer, off the North Slope, our ships have gotten down into temperatures below 0 degrees Fahrenheit. The chart on the right is a probability of exceedance chart that shows the expected probability of temperatures exceeding a plotted value over the course of a year at the ice edge. And I'll point this out later, but coincidentally with some design standards we have, there's a 95% probability that the minimum temperature will be greater than minus 40 degrees F over the course of a year along the ice edge. Getting into more detail on sea ice conditions, this is a chart that shows what ice conditions the ABS steel vessel rules ice strengthening classes are appropriate for. So across the top of the chart, it shows aerial concentrations going from consolidated to very open, and then thicknesses going from above 3.3 feet down to less than 1 feet on the left. And these areas that are highlighted in green, severe, medium, light, those are appropriate for the ABS ice classes A0 through D0 with the ship operating independently. So you can see as you get less concentration, a ship with a certain class can operate in thicker ice, and then higher concentrations, thinner ice. So the primary focus of the work we've done is to try to keep the open water patrol cutters safe. The WMSL is the Maritime Security Cutter Large, or the National Security Cutter. It's a 418-foot frigate-type ship that the Coast Guard is still taking delivery of. So the question that came to SFLC was, what are the maximum ice conditions for safe operation? So we looked at materials, and we looked at how the existing structure of the ship would be classed under the ABS ice classes. And then we did 2 successively advanced analyses of hull structural impacts with ice pieces. So materials first. These cutters were built by Ingalls. Materials not much different than what are used on a Navy Combatant, and all the materials are suitable for Ice Class D0, and they're suitable for Polar Class 7, which is the least capability polar class. I'm going to go through this a little quickly, but all the details are contained in the paper. The analysis of as-built ice classes, we looked at the shell plating and the stiffeners over all of the different regions of the hull that scantlings are specified for by the class. And the bottom line is that these cutters do not meet even the lowest class of D0 from ABS. So the plating thicknesses for D0, the actual as-built vary from 73% to 48% of the required thickness. And for D0, the stiffener sectional modulus varies from 35% at the bow to, what's that over there? I can't say, that's to 72%. So these results indicate the ship should stay away from ice, which was the first reaction that we provided to the operators. Since the Coast Guard's missions, there's always a trade-off between safety of life at sea and losses compared to risk. We started looking at ways we might be able to define the risk in a quantitative way if the ships do venture into different ice conditions. So we went through two different analyses. The first one we did in-house. It's plastic design analysis, similar to what the International Association of Classification Society rules are based on, which was based on some of the methods of Daly. And then more recently, we've had ABS working as a contractor to actually do some simulations with advanced failure criteria for thin ice, and also looking at the interaction between the ice failure and the structural deformations. So, method one results. The chart on the left shows the impact load versus ice flow size, 100 by 100 down to 10 by 10, ice thickness from 1/2 foot to 3 feet, and then ship speed from 0 to 20 knots. So you can see as you get back into this corner, the loads go up. So what we were looking for, what would be the limiting speed for each of these conditions, given the formation of plastic hinges in either the shell plating or a stiffener. The 6-inch ice, the 20 knots is probably not believable, but I think that the other ones you can see in 3 feet ice, 10 by 10 flow, the ship has to go 3 knots, and in a 1 foot thick flow, it's 5 knots. And so these are the limiting cases in the table at the right. The results from the more advanced method, where we're actually simulating the interaction of an ice flow elastically with the elastic hull structure, also end up producing limiting speeds. This work is ongoing, and these are early results, so it's not the final answer yet. The chart on the left shows limiting speeds for frame failure versus ice thickness. And this is all for 30-foot diameter ice flows. And so there's for a 1 foot thick ice flow, that's the load, and then this purple line is the limit state. And so then you can see that these are the limiting speeds across here. The other chart shows the limiting speeds based on hull plating. And this analysis just arbitrarily said we'll allow 2-inch deflection in any panel. So. Again, this methodology is still under development. We have to note that these are what are referred to as technically safe speeds. There are a lot of other factors that go into what safe speed would be in ice. This is technically safe from the standpoint of limiting hull deflection to some specified value. Comparisons with method one for shell plating are not valid, since that method assumed normal allowable plate deflections, where this one is looking at that 2 inches deformation, so it's showing higher speeds for a given ice thickness. In general, though, these results are encouraging and should provide more accurate method for assessing structural capacity for light structures and light ice. The method used by IACS, which is method one, is intended to be used for a heavy structure hitting large ice pieces, and it's assumed that the ice doesn't fail in buckling, that it's a crushing impact only against the hull. So it's a lot different for light structures. So for another project, for an early in-house design analysis of the offshore patrol cutter, we looked at what different levels of ice strengthening would cost and what they would buy us. As an example given here, weight increase for the extra steel varied from 2.3 to 3.1%, and costs, total ship costs, varied for an increase between 4.2 to 4.4%, which isn't much. So we looked at what does that buy you. These black areas these are the same ice charts I showed before, and these black areas show what we believe B0 might buy in terms of area, additional operating area, as compared to a non-ice strengthened ship. So it provides flexibility to the operators, but it certainly doesn't provide ability to go on long patrols into the ice. The other thing you have to keep in mind is that the ice conditions are very dynamic, and a ship that's operating in 30% coverage within a couple hours could be beset in 100% coverage, and so the operators have to be very careful. So experience with systems. I'm going to go through this pretty quickly. The details are contained in the paper. The design criteria for the national security cutters: seawater temperature minimum 28, air temperature minimum 0 degrees F for HVAC purposes, and minus 40 degrees F for deck equipment. Any mechanical systems exposed to ambient air temperatures outside. Coincidentally, that sort of lines up with that 40 degree F, minus 40 degree F temperature we talked about before. So keep in mind, these ships were not intended to be operated in sea ice or Arctic air temperatures, and they have operated as we just talked about. We looked at propellers, appendages, steering gear based on the ABS ice classes for ice strengthening again. Propellers meet class C0 as long as you keep the RPM down in maneuvering mode, not up at the higher RPM where we run on partially gassed turbine. The steering gear is designed for high speeds, and it should be adequate for slow speed operations in ice. And the rudder and other appendages face the same challenges as the hull structure, so they would have to be strengthened similar to the hull structure. The biggest problem the crews had during these operations were seawater systems. The ships don't include any recirculation of warm water back into the sea chests, so they have compressed air blowout fittings. The main diesel engines have 2 sets of flow restrictors that are supposed to be changed at some unspecified seawater temperature, so they had to experiment with that. And when they make any changes, they have to shut everything down, isolate the system, and close valves to do cleanouts and also to change those restrictors. So the recommendations here are, if the hull structure is deemed fit for any operations in ice, the seawater systems need to be upgraded. During the summer deployments in the high Arctic, off the North Slope of Alaska, machinery space temperatures stayed close to outside air temperatures. There's no heating in the machinery spaces, which was a problem. The current HVAC on the interior areas is okay for short periods below 0 degrees, but there were many areas where the crews were cold during those deployments. Deck machinery was another big problem area. Most of it was related to hydraulics on deck with no sump heaters, oils with too much viscosity, so machinery would have to be warmed up for a long time, and after you got it running, it would operate slowly. So we're changing over to low temperature lubricants and installing sump heaters and doing all the necessary stuff we can do to fix that. A major one that we found is the installed Mark 7 life wrap systems may not be suitable for an emergency if the air temperatures are below 22 degrees F, minus 22 degrees F. Also, maybe there should be more rafts, because if people have Arctic clothing on, they take up more space, and either more rafts or derate the existing rafts and add more. And finally, there was some work on towing systems. So conclusions. The Whimsical class cutters don't meet any ice classes. Recently developed methodology for structural analysis shows promise for quantifying the risk, which is what we need to do. Small gains in operating areas can be achieved reasonably, cost-effectively by going to something like ABS B0. A0 was not considered because it's a hull form change required. The Coast Guard's operational experience with any ships operating in Alaskan waters and ice is that conditions change quickly. Open conditions can quickly become closed. Ice pieces vary in thickness from half mile to half mile because of broken up pressure ridges, rafting, rubble fields. So even if even if the cutters don't operate in ice, we require that the shipboard systems be upgraded for these cold temperatures. So that was it. Is Larry Schultz in the room? No. Okay. We had two written sets of comments, but I'm going to hold off on those, and they'll just get published if we have questions that go 10 minutes. So.
Well, thanks very much, Frank. So, questions from the room?
Yes. As you said, they were not designed for operation in the Arctic back when they first started to build these. Are they going to, a couple of questions actually, are they going to consider upgrading the specs for any future? Are they going to build any more of these? Are they going to update the specifications so that they could be more attuned to the Arctic operation, do you know?
Okay. I have to repeat the questions for the recording in the back. So the question is the Coast Guard going to upgrade the specifications for these ships so they would be more suitable in the Arctic? And the quick answer is no. I think that they've got a contract, the construction contract is fixed the way it is, and any upgrades will be done after delivery.
Okay. I got a second question, which is how, when they're operating with these ships, your analysis is all about, versus thickness of the ice. How difficult it is to understand in the operation when you're starting to get with. How can you tell the thickness of the ice when you're operating?
That's a very good question, especially when the ice pieces may be broken up off of pressure ridges or they're rafted pieces. It's difficult. For an icebreaker, if you're going through solid ice, you can see the turned up pieces at the side, right? And that gives you a good idea. A lot of it has to be the experience of the operator. It's gray ice, it's real thin, or snow-covered thicker ice. So that's a huge issue, especially when you get up off the North Slope in the summer, and you may have pieces of multi-year ice floating down into the open water area between the coast and the ice pack. So, yes.
Your estimates on cost, about 4.4, I think you said, is that for new builds or for retrofitting the ones that are out there?
The question was, were the cost estimates presented in the paper for a new build or for retrofits? They were based on new build. They were based on something about 5 years ago that we did to decide whether or not the offshore patrol cutters should have an ice variant.
And a follow-up for that, have you looked into how much it's going to cost to upgrade the other systems as well? Because that was just a structural estimate, correct?
That was just a structural estimate. The other systems on the National Security Cutter are being upgraded no matter what the cost. So it's just sort of a sustainment cost that's factored into.
Any other questions?
Yes, ma'am.
What temperature did you start to see failures with the hydraulic systems?
The failures with the hydraulic systems are when you get down into the 0 to 10 to 15 degree Fahrenheit area. It's not really a failure, it's just a long warm-up period and a slow operation issue. So most of it can be covered with sump heaters and oil changes. Yes, sir?
What methodology did you use to do the deflection analysis?
There's a, ABS has been what methodology was used to do the deflection analysis? So for what we called method 1, was the same one that's used by IACS, and it's the load, either a point load or a line load, at which you first develop hinges in the plating or in the stiffener. And the plating always, it was like a center to help deflate. The stiffeners failed in shear failure at the ends before they, plastically, before they developed any other hinges. The second method is a simulation method that ABS at the Harsh Environment Technology Center has been developing, which is an actual simulation of an elastic ice flow hitting an elastic hull grillage and the ice fails either in crushing or buckling, depending on the thickness, and the hull deforms elastically, and then you specify the allowed deformation to get the limiting speed.
Finite element.
It's a combined finite element with the ice and the ship. So,
Just to the gentleman up the point in front of me's point about standards not being updated or
specifications.
specifications not being available. I know that for HVAC systems, there's a presentation tomorrow on app challenges and technical solutions for the Canadian Arctic program.
Right.
Ship it over, which may be interesting to mechanical system HVAC people.
Yep. So that comment was that there's a presentation tomorrow that may have some information on systems and HVAC this afternoon, actually.
Tomorrow. Yeah. Right.
Okay. Yep. Anybody else? Yes, sir.
Yes, sir. Has there any been consideration given to looking into the OPC contract to incorporate any of these changes, since the three designs haven't been finalized yet?
We can't really talk about the OPC because of where the contracting is, but I'll tell you what the history is. The history was that before the RFP was written, the Coast Guard did an analysis of alternatives, which I showed the results of in this paper. And apparently, the program office made, based on requirements versus cost, made the decision not to do an ice variant at this time. It may be something that they might want to do in a later flight of ships.
We'll take one more question.
In the well joint, normally have a very high residual stress. Have you, during the plastic hinge calculation, have you considered that?
I didn't hear the first part.
In the worthy joint, the frame or longitudinal frame, and in the very high residual stress, normally can get up to the ear point.
Right.
All right. So when you, during the calculation of the plastic hinge, do you take into consideration that situation?
It does go to yield, yeah, at that point,
And that,
right, at the hinge point, and then for the method one with the hinges, we limited deflection to like normal standards, like a half of a plate thickness or some percentage of span for the stiffeners. But it was plastic deformation.
Okay, well, thank you very much.